Hello, my name is Willie Johnson Jr., and I welcome you to the first in a series of lectures that introduces an exciting revolutionary approach to solving differential and integral calculus equations. This unique form of calculus is called Quaternionic Eulerian Calculus, or as I like to call it, QEC. QEC is a completely new approach to calculus that is based upon a fundamental redefining of the Newtonian limit. QEC is not the version of Eulerian calculus that uses Euler's method to find a good approximation of a derivative. QEC is completely different. QEC is exact. QEC is precise. QEC is based upon the algebra of the quaternion. One of the primary reference books for this course will be my recently published book, Synthesis. Synthesis updates several of the principles originally founded in my earlier book, Quaternionic Eulerian Calculus. Both books can be found at this URL. A brief word on my books. One should approach these books as one would approach beta testing a new piece of software. Unfortunately, you will find both typographical and factual errors. I published these books in less than ideal states to officially establish that it was I who was the first to invent and formulate these concepts and principles. The importance of establishing this provenance will become apparent once we begin our exploration of several mathematical conjectures. And incomplete though these books may be, they nonetheless afford the reader a first-time entry into a new and revolutionary discipline. For me, my books serve as quasi-journals or workbooks that keep track of my progress. My books are constantly being updated. Each book is the foundation for the next. Unfortunately, I just haven't had enough time to thoroughly and properly edit them. Most of my time and efforts have been spent in assuring that I first record and develop the mathematics at hand. I have paid little attention to the niceties of thorough editing and sales promotion. Of course, you are more than free to wait for a year or two until I have completed the entire editing process. For academics, such an approach may be unacceptable. However, you as my audience must first and foremost understand my ultimate goal. I am in the midst of trailblazing an entirely new path in mathematics. Unfortunately, this new path may at times be somewhat messy. It may not be pretty or readily accepted by some. But at its core, I'm confident you will find it to be groundbreaking. I'm inviting you to join me on this journey, and you will be rewarded with access to some of the most remarkable mathematics ever discovered. The second recommended book for the course is Arthur Latham Baker's Quaternions as the Result of Algebraic Operations, which may be downloaded for free and can be found on Google Books and a variety of other internet sites. A third book that I highly recommend, but isn't crucial, is Arnold and Maunder's Gyrodynamics. This book is particularly useful when we began exploring the practical uses of QEC. Each lecture or video will examine a chapter from Synthesis. I will proceed slowly in a logical, stepwise fashion. Hopefully, this will build a solid mathematical foundation from which we may apply our QEC principles. Now, the very mention of quaternions seems to strike fear and dread in the hearts of many math students as well as scientists and mathematicians. But please, do not panic. You do not have to have any knowledge about quaternions, and for those of you who do, you will find that we will probably use very little of what you may have been taught on the subject. It also is not necessary that you have any prior experience or prior knowledge of Newtonian calculus to understand this video or any of the other future video lectures on QEC. However, what is absolutely crucial is that you have a rock-solid foundation in both high school algebra and trigonometry. Being completely comfortable with applying these two subjects is essential. Without these two skills, you are just wasting your time trying to follow these lectures. It will be virtually impossible for you to understand and apply the concepts of QEC without these two critical skills. If you aren't up to speed, that's okay. Just stop here. Go brush up on your trig and algebra before proceeding any further. And when you know you are ready, come on back and join us. And now, without any further ado, let us begin our exciting journey on exploring the wonders of QEC. Here we see various charts of the trigonometric identities. There is no need to memorize these charts. However, from these charts, we are given three take-home messages. All trigonometric identities, including one, are equivalent. Any and every trigonometric identity, including one, may be expressed as a product or quotient of some two other trigonometric identities. Any and every trigonometric identity, including one, may be expressed as some function of the sine or cosine or tangent. Here we have a graph of y as a function of e to the x. But what does that mean? Well, it means a lot of things, but for right now, we will concentrate on only one aspect of this amazing graph. This graph demonstrates something rather remarkable about e. It illustrates that e to the x exists simultaneously as both point and area. Now at this time, don't bother trying to figure out how it does it, except for now, only that it does it. And for now, we assert that e as a point is a derivative, and that a derivative is a rate or slope or fraction comprised of y over x, and that an area is an integral or product comprised of x times y. Once again, we assert that the derivative of a constant is 0. And since e is a constant, then the derivative of e is 0, which means since the origin is 0, then the origin is the derivative of e. Another remarkable aspect of this graph is that it establishes that the derivative of e to the x is e to the x. Since the derivative of e to the x is e to the x, and if x equals 0, then the derivative of e to the 0 is e to the 0, which equals 1. Since the derivative of e to the x is e to the x, and if x equals 1, then the derivative of e to the 1 is e to the 1, which equals e. Since 0 radians and 2 pi radians are the exact same point on the unit circle, then plus or minus e as derivative must exist simultaneously as the derivatives plus or minus e equals plus or minus 1 equals plus or minus 0. Therefore, as derivative, e equals minus e equals negative e equals e star. E star is called the conjugate of e, and since e is equal to its conjugate, then e is declared as being self-conjugate. Since e is self-conjugate, then minus e precessing counterclockwise about the unit circle is equivalent to e rotating about the unit circle clockwise. And so, in summary, a derivative is a fraction. An integral is an area. Euler's constant e is a derivative. Why? Because it is a rate or slope or fraction of 2.718 over 1. Euler's constant e is also an integral. Euler's constant e always exists in a dual state. This dual state consists of both itself and its conjugate simultaneously. Therefore, e is designated as being self-conjugate. Euler's constant e is always self-conjugate. We will now introduce the QECian unit circle. We first begin by drawing a circle. we place a point at its center called the origin. The origin is always designated as being 0. However, in QEC, 0 is never null. There are no voids, no emptiness. There is only the 100% absence of something that is always replaced by 100% of its conjugate. Consider a conjugate as being an extreme. For example, a 100% absence of the North Pole precisely pinpoints its conjugate, the South Pole. The Argand diagram is incorporated within the circle, demarcating the x-axis and the y-axis. We next place the derivative of Euler's constant, e to the 1, at the origin. Extending right, we then extend e from the origin to its outermost extreme, this being the intersection of the x-axis with the circumference. At the circumference, e forms its conjugate e star, where e star equals e to the 0 equals 1. Therefore, e star forms a radius of 1. Since e is self-conjugate, then at the circumference, e forms a double point. Starting from the left, we extend e from the center to the circumference. This forms the cosine. Starting from the right, we extend the conjugate of e, which is e star, from the circumference to the center origin. This forms the versine. The versine is defined as 1 minus the cosine. The versine is also equivalent to the sagitta. A fully extended cosine and a fully extended versine spanning the space from center to circumference both form radii of 1. E may matriculate to any point within or upon the unit circle. We allow E to traverse along the circumference some radian arc length. Any such radian arc length, no matter its magnitude, is a quaternion. Therefore, any point along the circumference is a quaternion, as well as any 2 pi radian circle, as well as any object that may be measured in radians or degrees. Therefore, all platonic solids, conic sections, and any geometrical element constructed from these constructs may all be designated as quaternions. From some point along the circumference, we construct a normal extending from the point to the x-axis. This is the sine. From the origin, proceeding to the right, we draw a line perpendicular to the sine along the x-axis until this line intercepts the sine. This is the cosine. From the circumference, proceeding to the left, we draw a line perpendicular to the sine along the x-axis until this line intercepts the sine. This is the sagitta. The sagitta and the versine are identical, except the relationship of cosine to versine is horizontal, and the relationship of sine to sagitta is orthogonal. The versine and sagitta occupy the exact same space. The sine and cosine form a right triangle. The hypotenuse of this right triangle is the tangent. The sine and sagitta form a right triangle. The hypotenuse of this right triangle is the secant. The secant forms a chord which defines the extremes of the quaternion arc length, which by definition is a quaternion. From the list of trigonometric identities, I is always perpendicular to the tangent. Therefore, we may construct a right triangle whose base is a constant radius of 1, whose adjacent side is a varying I, and whose hypotenuse is of a varying length that extends along the x-axis. This length also forms a secant. We may also construct a fourth right triangle consisting of a varying sine base, a varying I hypotenuse, and a varying adjacent side that extends along the x-axis. This length also forms a secant. Several operations occur in the QECian unit circle acting synergistically and simultaneously. All processes begin at 0 degrees or 0 radians. They reverse at 180 degrees or pi radians. They then repeat at 360 degrees or 2 pi radians. Let's focus our attention on the unit radius, which is labeled as the black tangent. As the tangent revolves or precesses about the unit circle, its length always remains constant. Let's next focus on the red sine. Pay particular attention to its extreme ends. The sine grows from 0 at 0 degrees or 0 radians to a maximum length of 1 at 90 degrees or pi over 2 radians. It then returns to a value of 0 at 180 degrees or pi radians. The sine immediately reverses its direction of growth and once again reaches a maximum of 1 at 270 degrees or 3/2 pi radians, returning to a value of 0 at 360 degrees or 2 pi radians. The upper extreme of the sine accelerates and precesses along the circumference, while rectilinearly and simultaneously, the lower end of the sine accelerates along the x-axis. As the red sine accelerates across the x-axis, the versine increases in value while the cosine simultaneously decreases in value. When the sine reverses its direction of travel, going from left to right, then it is the versine that decreases in value as the cosine gains in value. Next, focus on the growth of the arc length or quaternion. As the tangent precesses about the circle, it grows the red quaternion. The same can be said of the sine. The red sine grows the red quaternion incrementally, forming the red circumference. Where the black tangent always remains constant, the green secant is constantly changing. At 0 degrees or 0 radians, it grows from 0 to a maximum length of 2 at 180 degrees or pi radians. It immediately reverses its direction of growth and once again reaches a minimum of 0 at 360 degrees or 2 pi radians. The red tangent as I is always perpendicular to the constant black tangent. This completes the QECian unit circle. In QEC, we will often designate the hypotenuse as being the tangent. However, the hypotenuse should technically be designated as the tangent line. Any and every point along the tangent line as hypotenuse is technically a tangent point. Therefore, a tangent line is a summation or concatenation of an infinite series of tangent points or tangents or tangent locations that sum or concatenate to form the tangent line as hypotenuse. The tangent is also defined as being a slope. A slope is the rate or fraction or quotient of a y value over an x value. Therefore, any and every point along the tangent line must be equivalent, since any and every such point must have the same y over x value. Therefore, any and every tangent point that lies along or upon a given tangent line is equal. The arc length may be considered as a summation or concatenation of an infinite series of points or e's or e locations as e propagates along the circumference. Since the secant is a hypotenuse and every point along the hypotenuse must be equivalent, then the chord is a quaternion since every point along the arc length is a quaternion since E is a quaternion. And since by the Pythagorean theorem, the secant is the sum of the sagitta and sine, then the sagitta and sine must be quaternions. Given the trigonometric identities, then the rate of sine over sagitta forms a hypotenuse, which is the secant. Therefore, the secant is a quaternion. And just as with the tangent, every point along the secant is a quaternion. And since the unit sagitta and unit cosine span the exact same length, then the sagitta and cosine must be quaternions. And given the Pythagorean theorem, where the sum of the sine and cosine equals the tangent, then the tangent must be a quaternion. And since all trigonometric functions may be defined in terms of the sine, cosine, and tangent, then all trigonometric functions and their identities are quaternions. And since E occupies a point on the circumference, then E and its conjugate are both quaternions, no matter their location. Therefore, any and every point within or upon the unit circle is self-conjugate E. Therefore, any and every point that lies within or upon the unit circle is a quaternion. Therefore, E, E star, I, pi, theta, 1, and 0 are all quaternions. Therefore, any and every point that lies within or upon the unit circle is a self-conjugate double point. Therefore, since any and every point within or upon the unit circle is equivalent to self-conjugate E, then any and every point within and upon the QECian unit circle must obey Euler's formula. The quintessential equation of QEC is Euler's formula, where plus or minus E to plus or minus I theta is equal to plus or minus cosine theta plus or minus var epsilon sine theta. The quintessential equation of quaternion algebra is the quaternion form of Euler's formula, where e to the I theta equals negative cosine theta plus I sine theta equals alpha beta is equivalent to beta over alpha equals gamma equals the tangent equals a quaternion, where in this case, alpha, beta, and gamma are all quaternions. These two equations correlate to what was deduced previously. All trigonometric identities are quaternions. Having allowed E to travel along the circumference to reach its final destination, several alternative paths were permissible, starting at the origin and traversing the tangent as radius, traversing the cosine and then up along the sine, traversing the cosine, then the negative versine, then up along the secant, traversing the cosine, then the negative versine, then up along the arc length. Euler's formula is both vehicle and instruction manual on driving E within and about the unit circle. It essentially says, I, you pull E up and down the sine, and theta, you rotate E about the circle, and both of you do it simultaneously. This is perhaps one of the most seminal principles of QEC. Just as E is simultaneously point and area, so too is E simultaneously arc length and line segment. Just as E exists as two distinct states, so too does it propagate throughout and upon the unit circle by at least two distinct modalities. To illustrate this duality of movement, consider once again the QECian unit circle. We will allow the quaternion I to precess the scalar hypotenuse 1 equals j into a unique position along the unit circle position k. That is, starting at 0 radians or 0 degrees, we will allow I to rotate the unit circle radius of 1, some angle theta, counterclockwise, such that the tip of the unit circle radius of 1 intersects the circumference at some point that is the confluence of I, pi, theta, the secant, and the tangent, where the tangent is equal to the hypotenuse, which is equal to 1. As I precesses the hypotenuse, which is equal to 1, which is equal to j, several other trigonometric operations also occur simultaneously. The sine, versine, chord, arc length, quaternion, secant, and angle all increase in both length and magnitude. The cosine diminishes proportionately in length and magnitude. The hypotenuse, which equals 1, which equals j, and the tangent, which equals I, both remain constant. The chord, angle, arc length, and the final point location of the radius along the circumference are all equal to the quaternion k. Therefore, ij equals k. which coincides with the take-home message of the trigonometric identities. All trigonometric identities are quaternions, and as such, must obey all the rules of quaternions pertaining thereto. Therefore, Ij equals k is a standard algebraic rule of quaternions. A derivative may be defined as the exact rate of instantaneous change. As I precesses j, which is equal to the radius, we may stop j at any instant we please. At this exact instance of instantaneous change, this instance corresponds to an exact and unique pinpoint location that lies along the circumference of the unit circle. This precise, exact pinpoint location along the circumference defines a derivative. The derivative is defined by the fraction or rate or a slope of the sine over the cosine. This rate is defined as the tangent. This rate corresponds to both the Newtonian and QECian expression of the derivative. However, QECian and Newtonian concepts of the derivative and limit differ, since any and all trigonometric functions are defined as being quaternions. Then by QECian principles and Euler's formula, any and all derivatives are quaternions. Thus is it established Quaternionic Eulerian Calculus. Any and every quaternion may be expressed as an arc length, and that arc length may be expressed in terms of a chord, which by definition is a secant. By Newtonian principles, a derivative may be generated by shrinking the chord or secant to zero, leaving only a single tangent point. By QECian principles, a derivative may be generated by shrinking the chord or secant to a double point consisting of both the point secant and its conjugate point, the tangent. This confluence of secant and tangent is clearly illustrated in the QECian unit circle. As I is rotated clockwise, the chord begins to shrink, as does the secant, which is equal to the hypotenuse of the similar triangle. The versine, chord, and tangent all converge at zero. The chord and versine shrinks to zero, just as the secant and cosine obtain a new value of 1. This is an illustration of the QECian limit. When E equals 0, then E star equals 1. Or when H equals 0, then minus H equals 1. Or when the versine equals 0, then the cosine equals 1. It is important to note that the Newtonian concept of infinitesimals and approaching zero does not exist in QEC. There is no dy over dx. There is no e approaching 0. There is no h approaching 0. There is no as e approaches 0, then e star approaches 1. Nor as h approaches 0, then minus h approaches 1. Nor as versine approaches 0, then cosine approaches 1. There is no gradually sneaking up on the function and hovering around and about it in some perpetual state of proximity limbo. The QECian limit is formed at precisely 0. It is also evident that just as the rate of the derivative may be defined as sine over cosine equal tangent, it may just as easily be defined as sine over sagitta equals secant, with the chord forming the secant line hypotenuse. Either interpretation results in the same pinpoint location of I or K along the unit circle. Therefore, the quaternionic version of Euler's formula is e to the I theta equals minus cosine theta plus I sine theta equals the product of alpha times beta, which is equivalent to the quotient of beta over alpha, which is equal to the product I times j, which is equal to the quotient j over I, which is equal to gamma, which is equal to k, which is equal to the tangent. The slope of the chord measures the rate of the growth of the arc length, which is equal to a quaternion, which is equal to the length or growth rate of the sine, which is equal to the rate at which the radius revolves about the circle. The negative cosine, which is equal to the sagitta, also experiences a growth rate as the sine accelerates to the left along the sagitta. The rate of the growth of the sine is not equal to the rate of growth of the sagitta. The sagitta measures the rate of E along the x-axis. The sine measures the rate of E along the y-axis, and the secant measures the rate of E along the circumference. The rate of the sine and the secant growth are equal. The rate of the cosine diminution and versine growth are equal. The positive slope of the unit 1 radius is not equal to the negative slope of the chord, even though both display an identical rate. This renders them conjugate slopes. Since they are conjugates, they form a derivative integral pair at the circumference. This must be the case since they intersect at the self-conjugate double point E. Therefore, E equals derivative and its conjugate E star equals integral or vice versa. Earlier we asserted, without any proof, that E existed simultaneously as both point and area. We can now see why this is indeed the case. E along the circumference marks an exact location as a point, but E also simultaneously indicates the length of its path along or upon the circumference. This path is an arc length, which by definition is a quaternion, which is measured in radians. But this radian path is not a straight line path. It is not one-dimensional. This radian path curves and therefore occupies 2 dimensions. This makes the radian path equivalent to a 2-dimensional area. Quaternionically, we may represent E as a point as the quaternion K. We may represent the 2-dimensional E as arc length, or equivalently as an area as the quaternion IJ. Thus, once again, we derive the fundamental Quaternion algebraic equation I times J equals K. Therefore, E exists simultaneously as both point and area, which reaffirms a basic tenet of Quick. E always exists in a dual state. Since E equals E star, then this double point, or this confluence or intersection of quaternions, is called the ICR, or instantaneous center of revolution, where E is equal to E star, which equals the ICR. Thus, at the ICR, the derivative and integral become indistinguishable, and this is the Eulerian fundamental Theorem of Calculus. We may also expand this definition of the Eulerian fundamental Theorem of Calculus. Given e to the I theta, we may simply express the exponent I theta as some variable x. And so we may express e to the I theta as e to the I theta equals e to the x. But as we have established, e to the x is the derivative e to the x. And so if we express a derivative as f prime of x and an integral as f of x, in either the upper or lower case, where in this instance x is the quantity or function that we are finding the derivative or integral of, then Euler's formula now becomes an alternative expression of the Eulerian fundamental Theorem of Calculus. This may be expressed as plus or minus e to the plus or minus x equals plus or minus e to the plus or minus I theta, which is equal to plus or minus cosine theta plus or minus bar epsilon sine theta, which is equal to alpha beta, which is equivalent to beta over alpha, both of which are quaternions, which is equal to an area, which is equivalent to a slope or a rate or fraction, all of which equal a point, which is equal to an integral, which is equivalent to a derivative, which is equal to integration, which is equivalent to differentiation, which is equal to E star, which is equivalent to E, which equals f of x, which is equivalent to f prime of x, which equals the conjugate of f of x, which is equal to f prime of x, which is equivalent to f of x, which is equal to the conjugate of f prime of x. Having now established some of the rudimentary rules and principles of QEC, let us now apply some of those same rules towards solving one of the most famous and long-standing conjectures in all of mathematics, the Riemann Hypothesis. The Riemann zeta function is an infinite series summation of reciprocals where each denominator is being raised to some power s. The summation of the terms on the right-hand side converge to form a limit. QEC finds a limit to be a derivative, or an antiderivative, or an integral, or a maxima, or a minima, or some example of an extrema, or an extreme. All of these I will further define in a later video. During the course of this proof, I will frequently qualify some of my statements with the term conventionally, because as I will demonstrate, conventional methods and definitions do not always apply to QEC, and so conventionally, the exponent s may be any number except 1 in order to obtain a convergent value. It is conventionally found that s, as any even negative number, will yield a value of 0. These derived zeros are called trivial zeros. There also exists a set of non-trivial zeros. And so the Riemann hypothesis essentially comes in two parts. Part 1 asks, what is the value of s when zeta sub s equals non-trivial 0? Part 2 proposes, prove that all non-trivial zeros are located along the critical line when zeta sub s equals non-trivial 0. And so now I present my margin proof of the Riemann hypothesis. Let's go through the proof step by step. Superimpose two unit circles. Shrink one of the circles eccentrically such that it is bounded by the points 0, 0 and 1, 0 along the x-axis. The innermost red circle is the space centroid. The outermost blue circle is the body centroid. Since the diameter of the body centroid along the y-axis is 2I, then the diameter of the space centroid along its y-axis is I. The diameter of the space centroid along the y-axis is the critical line. Since the diameter of the body centroid along the x-axis is 2, then the diameter of the space centroid along its x-axis is 1. In the body centroid, label point 0.5, 0.5 A, point 1, 0 B, and 0.5, minus 0.5 C. In the space centroid, the diameter I forms a hypotenuse of triangle ABC. This hypotenuse forms a tangent line. The origin of the space centroid coincides with the midpoint of the tangent line. Since in this case the origin is a 0 located on the critical line, then by definition this midpoint is a non-trivial 0. Since the non-trivial 0 lies upon the tangent line, then the non-trivial 0 is a tangent point. It is given that any and all tangent points that lie along or upon any given tangent line must all be equal. Therefore, in this case, any and every point along the tangent line is and must be a non-trivial 0. Therefore, I, the diameter of the space centroid, must be composed entirely of non-trivial zeros. Therefore, I equals non-trivial 0. 1 rotated twice by 2 applications of I operating on 1 yields negative 1. Therefore, if 2I times 1 equals negative 1, then I equals negative 0.5. Therefore, I equals non-trivial 0, which equals negative 0.5. It is given zeta sub 0 equals negative 0.5. Therefore, S equals 0, whereas zeta sub 0 equals I equals negative 0.5 equals non-trivial 0. And there you have it, an exquisitely simple proof of the Riemann hypothesis based upon some of the rudimentary principles of QEC. In our next video lecture, I will rigorously derive the QEC limit and provide several proofs of why Fermat's last theorem is negated.